So our speaker today is Aneesh Manohar from UCSD. He's one of our own. He was an undergraduate here. He graduated 1981.
Yeah.
In 1981, and then he went on to do his PhD at Harvard, and we actually overlapped there. I was a postdoc. He was a graduate student. And he told me some interesting things about Caltech back in the day. So at the end of this introduction, I'm going to switch from physics to a few facts about Caltech that I didn't realize that some of you might find interesting or amusing. We've written probably 15 papers together. We have a lot of common interests. Aneesh's physics is mostly on field theory and phenomenology or properties of elementary particles. Field theory is a tool that you use to explore them. And his work, the number of different topics he's explored in this way is vast. The properties of hyperons, baryons that contain a strange quark instead of just up and down quarks. Decays of hadrons. Hadrons are collections of strongly interacting particles that contain a heavy quark. Properties of hadrons that follow from very novel applications of the large number of colors limit, and the methods to derive those applications he and his collaborators developed. And they resolve some long-standing puzzles in the properties of hyperons. Aneesh's time at Caltech was, how could I describe it? Short. He got his degree in 2 years. He told me that when he came, he told, I don't know the person in that role.
Apostle. Tom Apostle.
Tom Apostle. He told Tom that, he knew all this introductory material. He didn't want to take the freshman and sophomore classes. And Tom said, okay, if you get into any trouble, then you can always take those classes after. And another interesting thing about Caltech at that time was, what do they call it? Is it called the graduation rate, the fraction of the students that enroll that end up finishing? Well, it ended up back at that time, a third of the people that started.
No, 2/3 graduated,
Yeah.
1/3 did not.
A third, I was going to finish with did not.
Yeah, okay.
Yeah, a third of the students that started did not graduate. And there was one more comment, which was even more astounding, which is, we have this orientation, I think we have it still today, where the incoming freshmen attend some seminars and do some activities to learn a little bit about Caltech life. So in one of these seminar type things, the speaker, like probably a Caltech faculty member or someone in Caltech administration, looked at the future student body and said, look at your student on the left. Look at your student on the right. One of you three will not finish at Caltech. So that's orientation. That's a welcome for the incoming student. So sometimes when the students I'm talking a lot about Caltech, and I have to fix it. Yeah. So sometimes when the students come to me and they say, oh, Caltech's so hard, and I try to be encouraging, but often I'll say, well, Caltech, we're the physics Marines. So if we're the physics Marines now, welcome Navy SEAL.
Okay, thanks for the introduction. What I was going to talk about today was angular momentum radiation, and in particular in electrodynamics and in gravity. And you'll see that there are some interesting features of this problem. So the work was started, I guess I'm going to have a hard time seeing the screen, but obviously, there has been a lot of interest in gravitational wave physics because of the amazing discoveries by LIGO. And it's important to get very accurate calculations of the radiation from binary in spirals. And the reason is that experiments can track the phase of the binary in spiral for many orbits, and a small change in the phase when you integrate it over many orbits can build up over time. And if you compute in an expansion in V over C, I was never able to find like a straight reference which tells me how many orders you need, but it looks like you need approximately 6 orders in V over C beyond the leading terms of the radiation, which I'll show you go like V over C to the 5th. So you need a very high order expansion. And a lot of people have been, including Cliff, for example, have been working on doing these calculations. So here's basically we're talking about this in spiral phase where you can track the oscillations for a long period of time. So the basic binary orbit from your classical mechanics is some elliptical orbit, and the parameters are governed by the total energy of the system, which governs the semi-major axis, and the eccentricity, which is related to the angular momentum. And so the energy radiation and the angular momentum radiation tell you how the eccentricity and A change with time. So the famous formula, which is the leading order formula, was due to Peters and Matthews from the 1960s, is essentially just taking so you can look in Misner, Thorne, and Wheeler, which derive the energy loss and the angular momentum loss. You integrate it over orbits. We'll come back to this formula, doesn't really matter, but just this is the formula which is used. And one point I want to make is that the angular momentum loss has one less time derivative than the energy loss. So the energy loss is 3 derivatives of the moment of inertia times the squared. And the angular momentum loss is 2 derivatives times 3 derivatives. We'll come back to this. So the binary pulsar was allowed one to test these formulae very accurately. So Hulse and Taylor discovered a binary system, and then the orbit of the pulsar slows down, well, speeds up. Actually, the radius comes down because of energy dissipation. And here is their measurements of the phase of the orbit over many years compared with the GR predictions. And it's basically right on top. And at least from their review paper, they agree to 0.1%. Now, in this binary system, V over C varies. The orbit eccentricity is, I think, 0.63 from 10 to the minus 4, between 10 to the minus 3 and 10 to the minus 4. So you are not going to really test high order corrections in GR from this, because typically they'll go like V over C squared, and they're tiny corrections. But it turns out then the gravity wave from the binary in spiral, you are following the in spiral all the way in until the system becomes nonlinear, and you have much more. You have access to many high orders in V over C. Okay, so let me first start with something you're familiar with and which will lead to an intuition which turns out to be incorrect, which is angular momentum as done in physics 1. So you have a bunch of particles moving. The angular momentum is r cross p. And angular momentum depends on the choice of your origin. And if you don't have any coupling to anything else, the angular momentum, there's a conservation law for angular momentum. And for the later formula to be more, the notation I will use in the later formula is, rather than use a cross product is special to 3 dimensions. It's really, you should think of it as an anti-symmetric object with 2 indices on it. And so the z component of angular momentum is really the xy version, which is xpy minus ypx, for example. And these square brackets just mean anti-symmetrized in the indices. So just think of angular momentum as a 2-index anti-symmetric thing rather than a vector. And then if you can always decompose this angular momentum for a mechanical system into something you can call the orbital angular momentum and the spin. The orbital angular momentum is related to the motion of the center of mass and depends on the origin. And here P is the total momentum. And then the spin is you can think of as some internal angular momentum, which is independent of the origin. So if you have a gyro like this, then the spin part is, due to this disk spinning, and then the orbital part is like the entire gyro moving through space. And unless you're in the center of mass frame, the total angular momentum, this one, the orbital part, depends on the origin. So now we can try and extend this to electrodynamics. And you might think you can do something very similar. We would like to write down the angular momentum of the electromagnetic field as some combination of orbital and spin angular momentum. After all, photons have helicity. They have spin plus or minus h bar. And so that should maybe correspond to spin angular momentum. And then the orbital momentum of fields is related to the angular dependence. And maybe it should be related to theta and phi derivatives of the electromagnetic field. After all, gradients in quantum mechanics are the momentum components. And so theta and phi would be the angular directions. And you would want it to be gauge invariant so that different people agree on what the momentum, angular momentum is. And of course, you need the conservation law that at least if you have E and M coupled to charged particles, the total angular momentum of the whole system is conserved. So let me start with something which I didn't know was called Feynman's Paradox until I was starting to look at some papers. But this is, okay, this is taken directly from the Feynman Lectures on Physics, Volume 2, which is you have a solenoid with a magnetic, so there's a magnetic field in there. There's a bunch of charged particles around it. And then, so if you want to do it in the more sophisticated form, it's a superconducting solenoid. You slowly warm it up so the magnetic field goes away. Nobody's touching the system. And the question is, will the disk rotate if the current is stopped? And given that this is the question, the answer is yes, because otherwise, why would it be there? But how do you calculate that? Okay, and this is just, okay, so we're doing physics, whatever, physics 1 or physics 2, depending on where you're, which year you do E&M. But you take Faraday's law that the line integral of the electric field is to the rate of change of magnetic flux. And you find that outside you get an electric field which is proportional to 1 over r. The charged particles have a force on them, which is QE. And so the angular momentum transferred has an extra factor of r. It's going to be important that the product is independent of r, and you get some angular momentum. And now the question is, where is this angular momentum? So that was what the Feynman lectures had. And it's not due to the current in the solenoid. If you take a gyroscope which is spinning and move it around, you'll feel the torque in your hand. If you take a solenoid which has got current flowing in it and move it around, you don't feel any torque. Definitely the angular momentum is not due to the electrons moving in the wire in the solenoid. And another way to see that is that the angular momentum is proportional to Q times B. And if I flip the sign of Q, the disk will spin the other way, but the electrons in the solenoid are still moving in the same direction. And in the initial configuration, which is here, nothing is changing with time. There's some static electric field, which is a constant, and there's a static magnetic field. Nothing is changing with time. And nevertheless, the system has angular momentum. And so the resolution of this is there's some angular momentum, there's some flow of energy and momentum in the electromagnetic field. Okay, so let me back off for 1 second and discuss something else which is going to be related, which is what is a conservation law, because we would like the angular momentum to be conserved. So in relativistic theories, you have a local conservation law, which says that the divergence of the current is 0. And that means that if I go to 3 vectors and whatnot, and away from the 4 vector notations, that the rate of change of charge density for plus the divergence of the current is 0. And that means that the local change in charge is related to the current flowing out. A global conservation law would be like a charge at one point in space jumps all of a sudden to a different point in space. The total charge would be conserved, but that's not a local conservation law. And you cannot have that in relativity because a different observer, what is simultaneous to one observer is not simultaneous to another. So you always have in field theory, the conservation laws are local. And if I now integrate this over a big cylinder in space-time, so this is 4 dimensions if you want time and space, you can convert a divergence to a surface integral. The integral over the top cap is like the charge. The normal in this is in the time direction, so you get the charge, or J0, integrated over the volume. The integral over the bottom cap is also the charge, but at time minus infinity, and the normal is in the opposite direction. So you get Q infinity minus Q minus infinity. And the sides as the integral of the flux escaping integrated over all time. So what we're looking for are laws like this, which say that the change in whatever conserved quantity I have is given by some integral of a flux.
Hi, Aneesh. So sorry to interrupt, but we're not able to see the slides that we're only seeing the introduction slide.
So interesting. Okay, is it changing?
No, it's still on the introduction slide.
Well, should I stop share and restart?
Yeah, so the slides aren't progressing forward for the people on Zoom.
Okay. Let's see what.
Let me try it again.
Oh,
Now does it work?
Yes, now I'm seeing it. It's going from the angular momentum transfer to the where is the angular momentum.
Okay.
Yes, yes. Thank
Great,
you.
okay.
Thank you so
Thanks.
much.
Yeah, it's good I had my volume on. Okay. All right. So there's a nice way to calculate the energy momentum tensor for any field theory if you're given a Lagrangian or an action formulation. So here's the action for electrodynamics. If you know it in curve space, which is you simply vary the action with respect to the metric tensor, and there's some normalization convention, but the coefficient in front is the stress tensor. And it's gauge invariant because the Lagrangian itself was gauge invariant. It's symmetric because you're picking out the coefficient of G mu nu, and G mu nu is symmetric. So what you get out is symmetric. And you can show by using the fact that the action is diffeomorphism invariant, that whatever tensor you get out is conserved. I'll come back to this. It's covariantly conserved. But if you work in flat space, you get the standard conservation law that d mu t mu nu is 0. So here's what the stress tensor is for E and M. And if you work out the components, you get, well, this should be familiar to everyone. You get a half E squared plus B squared. There's some normalization depending on whether you use Gaussian units or SI units or whatever. But E squared plus B squared, you get a flux. You get a momentum density in this corner, which is equal to the energy flow, which is E cross B. This is the Poynting vector. And then you get some stress tensor. So if you think of what T mu nu is, there are 2 indices on it. One of them is whether you're looking at the 0 component or the space component, it's the energy or the momentum. The other one is telling you if it's the 0 component, it's the density. And if it's the space component, it's the current. And this object shows relativity in a very nice way because what the columns or the rows, whichever one it is, the columns have unified energy and momentum. The rows have unified space-time, or effectively the density and the current. And then every term in here has E's and B's. And so you have a sort of a unification of electric and magnetic fields. So you can see relativistic invariance right there. And once you have an energy momentum tensor, you can write down an angular momentum tensor, which is basically like a cross product. That's why I've mentioned this antisymmetric combination of the coordinate with the energy momentum tensor. So the first index mu tells you whether it's mu equals 0 is the density and mu equals I is the current. And then these 2 indices tell you which component of angular momentum it is. So Jz would be nu is x and lambda is y, et cetera. And if you just take its divergence, because the energy momentum tensor is conserved, the only derivatives can act on are the x nu and the x lambda, and you get t nu lambda minus t lambda nu. And if T is symmetric, it's automatically conserved. So you know what the angular momentum is. And you can't have multiple angular momenta conserved because otherwise you wouldn't have scattering or any non-trivial processes happening if you have an extra independent quantum conservation law. So this is the angular momentum for electrodynamics. And if you work it out, the density of angular momentum is r across the Poynting vector, as you might expect. So the Poynting vector is like momentum flow, and r cross it is like angular momentum. And one thing I want to emphasize is this looks like the old formula for orbital angular momentum, r cross e cross b, because this is like a momentum. There is no spin term. So this idea that you have an orbital plus a spin piece is simply false for E and M. This is the total angular momentum. It includes the spin of the photon, everything is in there. Okay. So this intuition that there could be a spin contribution from the photons having spin 1, there's no extra piece. It's all in this contribution. So now let's work out a calculable version of Feynman's paradox, which is, here's my solenoid, it's a cylinder. And instead of having this charge distribution, which I can't calculate with, I'll have two cylinders of charge, one with a charge Q and one with charge minus Q. And you can see that there's a radial electric field for the two cylinders. There's a magnetic field in the z direction. So this is looking at the system from the top. And E cross B flows in a circular direction. And so we have momentum flow, even though nothing is changing with time. Okay, I just want to emphasize E and B are time independent, but there's still momentum flow and therefore angular momentum flow. So you can work out, first of all, if the magnetic field slowly changes or decays from the value of B to 0, you can work out by Faraday's law, the thing I showed you, what the electric fields are. The field outside is what I had before. It falls off like 1 over r. We'll need this later. The field inside, because the flux inside is smaller, it's just the area inside that counts. It goes like r. So I will give this as all a homework problem. You can verify these equations. The angular momentum transfer to the inner cylinder is from the torque. So there's a tangential electric field. The force is QE. And you integrate it with r, and you get some value. For the outer cylinder, you get basically you replace r1 by r2 and flip the sign because the charge is opposite. So you get that. And if you integrate E cross B between the two cylinders, which is the only place where you have both an E and a B, you get exactly the right angular momentum to equal this. So as Feynman wanted you to figure out in his volume 2, there is an angular momentum in a static electromagnetic field, which gets transferred to the cylinders. Now let me move the outer cylinder to the edge of the solenoid. Well, that's trivial. I just replace R2 by A. And in the formula of the field, I replace R2 by A. Again, the angular momentum is conserved. OK, now let me move the outer cylinder outside the solenoid. Now, E cross B only exists inside, so this integral doesn't change. But we saw that when we did the angular momentum calculation outside, the electric field went like 1 over r, so the torque was independent of radius. And so the torque at this point is the same as if this thing was at the edge of the solenoid. And so again, you get angular momentum conservation, because it doesn't matter where the outer cylinder is. Now I remove the outer cylinder, so it's not there anymore. So now this piece of angular momentum is missing. So what happened to that? Well, so that's what I just said. What happened to the conservation of angular momentum? Well, there has to be a flux of angular momentum flowing all the way out to infinity. And if you work out what the flux is, it's the radial flux you need, and it turns out to be r dot E times r cross E. And so in our problem, we need an electric field which has a non-zero dot product with the r hat, the radial direction, and has a non-zero cross product with the radial direction. And what you get are two contributions. we had the original, we had the electromagnetic field, the electric field from Faraday's law, which is going in an azimuthal direction. That contributes to R cross B. But we had the static radial Coulomb field from the cylinders, and that contributes to R dot EC. And so what's important here, and it'll be relevant later, is you get an interference term between a static Coulomb electric field and this magnetic field from Faraday's law. And the net result gives you the correct angular momentum flow. Okay, so one of the things you can do here is, because the Poynting vector E cross B only exists inside the solenoid, there cannot be any energy flux leaving the cylinder and going to infinity. And so one of the things you see in this example is you can have angular momentum flux without having any energy radiated. So you can get rid of angular momentum with no energy loss. And this is very different from your naive view of, say, if I went to a spherical geometry where I have radiation and I have electric fields falling off like 1 over R and magnetic fields falling off like 1 over R, the energy flux, which is E times B, falls off like 1 over R squared. And so the area, the surface area goes like R squared. So you get finite flux going out. But angular momentum has one extra factor of R. So you need not just the electric and magnetic fields to 1 over R, you need them to 1 over R squared. And that includes the Coulomb electric field, and they contribute to this flux out. So the standard intuition of this energy flowing out, which is causing angular momentum loss, is not correct. So now I can switch to gravity. And I want to do the analog of the electromagnetic stress tensor or the electromagnetic angular momentum for gravity. And so these are the basic equations of GR for gravity. And one of the consequences of this, which I briefly mentioned, is it turns out that you're working in a curved space and the stress tensor is covariantly conserved. This is a covariant derivative, not just a partial derivative. And you might say, OK, let's define the momentum by integrating, just like you would in flat space, T0 nu over the momentum. But this does not produce a conserved quantity. And in fact, this object is kind of meaningless. Because for using Gauss's theorem and so on and integration by parts, you need an ordinary derivative d mu, and a covariant derivative is not good enough to allow you to get that the change in energy and so on is related to the flux. And you cannot define angular momentum this way either, because x mu in flat space is a tensor, but in curved space, x mu is not, it's just a coordinate. It does not transform as a tensor. And so this object is some meaningless thing, or not meaningless, but it's coordinate dependent. So there's no different people using different coordinates would not agree on what the angular momentum is. OK, so energy in this problem is being transferred between matter and gravity. So maybe you can try and write a total stress tensor, which is just the matter part, which is the right-hand side of Einstein's equation. But maybe there's a way to write down a gravitational contribution. And just like the electromagnetic and stress tensor, it depends on E's and B's, maybe the gravitational part depends on gradients of the metric, first derivatives of the metric, just like E and B are first derivatives of the vector potential. Well, this doesn't work. And the reason is the principle of equivalence says that you can always go to a local inertial frame, or equivalently, you can always go to Riemann normal coordinates where the metric is the flat space metric and the first derivatives vanish. And so whatever definition you have for this, somebody using a coordinate system can set it to 0. And so point by point, you can make it 0, or at least you can pick a coordinate system which depends on the point where you could set it to 0. So this is not well defined. And its integral is not well defined. But we're OK, so you might say that all hope is lost, but that's not true, because you can look at, for example, what Cavendish did when he weighed the Earth. He did not find the mass of the Earth or the energy of the Earth by taking the T00, the energy density, that is slicing the Earth into little pieces adding up the sum of the masses and getting the total mass of the Earth. What he did instead was use the fact that far away from the Earth, the fields are weak and the gravity can be linearized. And weak here means you're far away compared to the Schwarzschild radius, and the Schwarzschild radius of the Earth is 9 millimeters. So the surface of the Earth, even though you're right next to the Earth, in the gravitational sense is far away. And you can show that the asymptotic metric far away, so this is all taken from Mishnathorn and Wheeler, can be written as flat space metric plus some corrections, which are telling you the mass in the dt squared and dx squared terms. And then in the cross term between dx and dt gives you the spin of the system. And so if you have asymptotic flat space, so you have Minkowski space, it doesn't matter what's in the inside. By looking at the metric far away, you can define the mass and the angular momentum. And experimentally, that's what you mean by the mass and angular momentum anyway, of the sun or something. You're not going inside the sun and measuring the mass. You're looking at the effect of the sun on planetary orbits. And that's coming from the asymptotic metric. So if you look at asymptotic Minkowski space, you can take Einstein's equations and linearize them by expanding, writing the metric as eta mu nu plus h mu nu and expanding out. And the linear terms you keep on the left-hand side, and all the quadratic and other terms you switch to the other side. And call all the quadratic and higher order terms T mu nu gravity. And the linear term you call is turns out to be this. It's some combination of the stress tensor, the metric and its two derivatives. And my notation here is that this object, which you can see explicitly, is antisymmetric in mu and alpha, and it's antisymmetric in mu and beta. In fact, it has the same symmetry properties of the Riemann tensor. It's symmetric if you switch mu alpha with mu beta, etc. So now this object is conserved because similar to the way the electromagnetic current is conserved, the electromagnetic divergence of F mu nu is J nu. That's Maxwell's equations. If I take another derivative, because F mu nu is antisymmetric and partial derivatives commute, the left-hand side 0, which leads to current conservation. And from this, because there's a divergence here, you can use, again, Gauss's law and get the charge inside by integrating the flux of electric field. So you can find the charge of a system by looking at far away, by looking at the electric fields far away. This is like two copies of the electromagnetic equation. There are two derivatives, and there's two sets of antisymmetric indices. And so we can measure the momentum and angular momentum in terms of the gravitational fields at infinity. Everything transforms as Lorentz transform tensors at infinity because you're back in flat space. And you can define angular momentum because x mu is a tensor at infinity. So the summary is, again, you can read all about it in Mishnathorn and Wheeler. You can define a tau mu nu, which is conserved, and use it to do everything you wanted about angular momentum. Different observers will disagree on where the energy is distributed, but the total integral, the total momentum and the total angular momentum is independent of the observer. And you get the usual conservation law that the flux of energy out is the change in the energy or the mass inside, provided the mass inside is measured gravitationally in terms of the asymptotic field. So this does everything you want. And there has been lots of confusion about this in the past. And in fact, Feynman went to a conference where there was an argument as to whether gravitational fields carry energy because it's geometry, and how can geometry carry energy? And Feynman did one of his classic things, which is he just looked at gravity waves going past two masses on a spring and showed that the masses oscillate, and showed that, well, you can do work, so it must carry energy. And apparently the response was, Feynman, gravity is too subtle for you. Now, there's lots of Feynman stories, but here is a letter from Feynman to Weisskopf. Okay, and for the students in the audience, this is not a LaTeX font. Okay, this was actually typed on a typewriter, which you may not have seen over a period of time. And there's some interesting things in the letter. So for example, apparently the people were arguing with him that how can you treat gravity as a perturbation on the proton, even though, m proton over m Planck's 10 to the minus 38. But then, I'm not going to go through the whole thing. Okay, this is page 13 of the letter, but he's computing gravity waves going past an oscillator and getting the response. And then he said, I'm surprised to find a whole day at the conference devoted to this question that experts were very confused. This is what comes from thinking about conserved tensors instead of can the waves do work. And finally, maybe the last sentence is the most relevant. It said, isn't it interesting to live in our time with such nice, wonderful puzzles to work on? And then there's a follow-up, which is he got invited to a conference in 1966, where he says, I'm not interested in what today's mathematicians find interesting. Okay, so what I wanted to do in the last bit of the talk is discuss some recent work on gravity. And to do that, to explain what's been done, I want to first discuss what's called the PN expansion. So if you have a gravitational system or just a circular orbits, the velocity and gm over c squared. So pretend all the masses are the same. We're not going to worry about big mass ratios or anything. This combination, which is the Schwarzschild radius over r, and v squared over c squared are the same order. And the PN expansion counts factors of r Schwarzschild over r, or factors of gm over r as 1, and v squared over c squared as 1. So 1 PN means one more factor of one of these things, etc. We'll see that there are some effects which are odd powers of v over c, and they give you 0.5 PN because it's half of that. So the recent progress in gravity, or sorry, in this problem, has come from applying effective field theory methods and diagrammatic expansions to what is really a classical problem, where you might think that maybe a better way to do this is just perturbation theory on field equations. And it starts with some work by Goldberger and Rothstein, where they say we're interested in gravity far away from these objects. It doesn't matter whether it's the sun or whatever. If you're probing the sun or measuring the gravity of the sun from the distance of the Earth, the sun is effectively a point mass. And I mean, that's what you do when you're doing classical mechanics. So we can treat gravitational objects as point particles with internal structure of the objects treated as higher dimensional operators. So for example, you can distinguish a black hole from a neutron star by looking at an R² coupling to this, which is a higher dimensional operator, and something called the Love number. And this is very analogous to the use of effective field theories in particle physics, where if there was the electron is treated as a point-like particle, and if there's some new interactions at some high scale, you can include the substructure of the electron by putting in higher dimension operators suppressed by 1 over m. What's surprising here is a black hole, a 30 solar mass black hole is a point particle, or a 30 solar mass, well, whatever, or the sun's a point particle. And that's because we're probing it at much further distances than the radius of the object. So it's effectively a point particle. The other thing you can do is use Feynman diagrams and scattering amplitude methods to calculate basically energies and potentials and so on. And so if you look here at a one graviton exchange, each graviton vertex is square root of g. So this is sort of giving you the PN expansion if you want. So the Newtonian potential is one graviton exchange, you get a factor of g. If you go to 2 graviton exchange, you get the Einstein-Infeld-Hoffman, which is the 1 PN correction, and so on. The other maybe non-intuitive thing is people decided to go to look at scattering instead of bound state orbits, where you can treat the velocity and the radius as independent. So you can have a particle coming in and another particle in the opposite direction. I've drawn this in the center of mass frame, and they scatter. And the variables of this problem are Newton's constant, the impact parameter, effectively the radius, the mass of the particle, and the momentum of the particle. And the momentum transfer. So in field theory, we don't look at impact parameters or anything. We're just looking at the momenta of the particles. You can't measure in quantum mechanics. You can measure position and momentum at the same time. And there's two kinds of momenta. One is the momentum transfer, PF minus PI. And the other one, if you want, is the magnitude of PI or the magnitude of PF. And I'll try and be a little careful here. So PF minus PI can be written as h bar times q. So q is a wave number, and it differs from momentum by a factor of h bar. And q is the Fourier transform of r. So the scattering amplitude can be written in terms of q. So G, Q, M, and P. And now you can ask, what are my expansion parameters? So I take these variables, and h bar and c, and look at what the dimensionless parameters are. And one of them you can construct is R Schwarzschild over R, which is in the units, in the way I'm writing it, is GMQ over C squared, because 1 over R, R is conjugate to Q. V over C is simply the momentum of the mass. And the other one is the mass of the object over M Planck. And now you would say, okay, well, for the sun, for example, M sun over M Planck is 10 to the 37 or 10 to the 38, and therefore quantum gravity must be important. I mean, that's clearly absurd. And the answer is this is not the right parameter to use. The real parameter we need, because we're working about the classical limit, is the ratio of h bar, which has units of angular momentum, to the angular momentum of the system, which is q over p with an h bar in here. And for the Earth going around the sun, this ratio is 10 to the minus 75. Okay, so remember that Bohr started with the hydrogen atom and semi-classical quantization by looking at orbits with angular momentum nh bar, and in hydrogen, n starts at small numbers. Here, we're looking at the limit of very high quantum numbers of 10 to the angular momentum is 10 to the 75 units of h bar. What we want is the classical limit. So even though we're doing Feynman diagrams, the Feynman diagram has the full quantum physics in it. We don't need all that information, so we can expand in powers where we expand in q over m, because q over m or q over p is basically the h bar power counting parameter. So the way you take the classical limit is you look at the diagrams, you expand in q over m, throw out all the high order terms in q over m. It makes the integrands easier, and you do the integrals. There's another subtlety with taking the classical limit from quantum mechanics, which is you can't just take the limit h bar goes to 0. If you look at the WKB approximation, the wave function is written as e to the I, the exponential of s over h bar. And it's s, which has a power series expansion in h bar. If you were to expand this thing out in a power series first, you would get 1 over h bar squared, etc. So the wave function does not have a smooth limit as h bar goes to 0. It doesn't have a classical limit. It's the exponent which has a good limit. And so you have to take the log of the wave function and then take the classical limit. Otherwise, you can't recover the classical result. If you look at potentials from Feynman diagrams, for example, which is again like one photon exchange or one graviton exchange, 2, etc., they build up to give you an amplitude, which is e to the minus whatever the potential is times the time over h bar. And again, if I start expanding this in a series, I get t terms, t squared terms, etc., and I get 1 over h bar squared, etc. Now, in quantum field theory, the fact that there's a t here is a standard infinity, which we throw away, which is a delta function of 0, omega equals 0. But t squared terms are more singular and lead to Feynman diagrams, which are infinite because of something called pinch singularities. But here you can see this as these photons could be arbitrarily far apart, and you get a factor of infinity from the diagram. And so you can't actually do this diagram. It's sick. And you get, as I said, you get what I call super classical terms. You get terms which are 1 over h bar squared. And the resolution to this is the same as the WKB approximation. You first take the log of the amplitude where all of this goes away. You just have this exponent and then take the classical limit. And this was done in NRQCD and other things. And I'm simplifying things here. This took many years of work and to sort all of this out. And doing the diagrams is not quite as, well, it takes a lot of effort. So I'm just simplifying that. So the field theory method was done by a lot of people. I'll not go through all of this, but if you look at it carefully, you will see that, like, I don't know, 80% of them work from Caltech. The rest, I think, are from UCLA. So, and what I'm going to talk about the work I did, which was with Alec Ridgway and Jia Xian Shen. They were all students here. One, Alec was with Mark Wise, and Jia Shen was with Cliff. So let me show you what's, I have time, yeah, what was done with the interaction potential. So the leading term is the Newtonian potential Gm1 m2 over r, and I'll factor that out in my counting. Some people include this, in which case something which is order 1 should be treated as G should be G² etc. But I'm doing it relative to that. The standard 0 pn is Newtonian. 1 pn is high order, one high order in G or one higher order in V². Here's 2 pn, 3 pn, etc. And 0 pn was Newton. 1 pn was a little bit later, Einstein, Infeld, Hoffman. So whatever, 250 years. Yeah, 250 years later, and then progress speeded up. So the 2 pn is like 1980, etc. And this is state of the art, 5 pm. That's been done. Now, by the field theory method, you can, because you're using relativity, you don't have to do the expansion in V over C. And so you can sum the entire row. I don't know who did the order 1 term, but the order G term was, well, Cliff did this, and also Westphal. And then, so the heroic work has been to do the G² and the G³ calculations, which have been done very recently. And so it gives you a lot of information from here, including many of the higher order PN pieces. Remember that if you go to 6 orders, so V over C to the 5th times the extra V over C to the 6th, that's you're like 5.5 PN, or you need some of these terms for the gravitational future of gravitational wave experiments. So there was an extensive literature on the PN results. I'm not with Damour and people. I mean, this is extremely important work. I don't want to, but I'm not, well, Blanchet and Damour, and then Buonanno and company have figured out how to generate waveforms from the potentials and so on. But I'm focusing more on the field theory way of calculation, so I'm not going to discuss this more. So let me look at the angular momentum and energy loss in the PN formula. So this is the original Matthews-Peter calculation, Matthews and Peters. So the moment of inertia goes like mass times r². So the first derivative, if I differentiate that, goes to mass times rv, because r. If I differentiate a second time, I get a term which is v², where both derivatives act on 1r, or anyways, you get v² and r times a. But the acceleration in a gravitational system is gm over r². So you get 2 kinds of terms. You get a v² term and a gm over r term. If you differentiate one more time, the triple derivative, in here, both of them end up giving you the same kind of structure. So you get a gm v over r² here. So I hope I did this right. So if I now look at energy radiation, which is the third derivative of the moment of inertia squared, so this is the Matthews and Peters formula, and I rescale it by multiplying by the time of the orbit divided by the average energy of the orbit to get something dimensionless, and you work it out, you get 3 factors of gm over r and 1 factor of c over v. So in short, it's g³ over v, and this is 2.5 pn. It's 3 pn from the g³ and minus 0.5 pn from the v. If you do the same thing with one I double dot and one I triple dot, you get two kinds of terms because the two here, two kinds of terms there, you get a term which is G squared V and a term which is G cubed over V. Both are 2.5 pn because the V squared counts like a G. So if you look at order G squared, you can see from here, you're getting angular momentum loss at order G squared. You're getting no energy loss at order G squared. Energy loss starts at G cubed. And then at order G cubed over V, you get both. So again, I think about, well, Caltech, Enrico was a student here and Julio is a postdoc here now, worked out the energy loss to order G cubed, but to all orders in V. And what we worked on was to work out the angular momentum, both to order G squared and G cubed, but to all orders in V.
So is the G squared compared to the G cubed for energy, is that a reflection of what you said at the beginning?
Yeah, that's this one extra R, yeah. And so, yes, that's right. It's coming from that. And well, let's just, yeah, so there were mistakes in the literature because of this. So if you look at this general scattering again, we can do something which particle physicists are familiar with, which is write the kinematics in terms of form factors. And if you work it out, the basic, the separation between them can be written as a piece which is delta B, which is the impact parameter. And you can write B bar, which is, this looks very complicated, but what this is the center of mass position of the system, written in a relativistically invariant way, so you can go from one coordinate system to another. The total momentum radiated is some function of the vectors in the problem, which are P1, P2, and delta B. It cannot depend on B bar because the momentum radiated is translationally invariant. If I move the system, B bar changes by my translation parameter, and this can't depend on that. F1, F2, F3 are, I'll write down the variables. The Lorentz invariant form factors, I'll write down the variables. The angular momentum is this two-index antisymmetric, this is running out, but is a two-index antisymmetric tensor. And there's a B bar piece, which is the statement that if I translate the system, the angular momentum changes by the translation cross the momentum radiated. And then there are two other pieces. So there's these bunch of form factors that you have to calculate. And you can expand them in powers of G. And the independent variables I wrote down here. Let's see if this is battery is recovered. The main non-relativistic parameter, which is sigma, is the boost factor between it's P1 dot P2 over M1, M2, or what's called W in heavy quark effective theory. It's the boost of particle 2 as seen in the rest frame of particle 1 or vice versa. And F, the momentum, has no piece at order G squared. It starts at order G cubed. So I'm going to just, okay, so now there's a lot of work which goes into this. I'm not going to discuss it, but I'll just give you the results. So at order G squared, I'll give you what these functions mean in a second. I just want to prove that we did something or somebody did something. So here are the form factors in terms of mu, sigma is the boost, and there's some integral here, which I'll discuss. And at order G cubed, the energy loss is given by this, and there's some functions here for, these are the functions for the angular momentum loss. And then here are what the functions look like, okay? And these blue things, F1, F2, F3, came into the energy loss formula, and all of this stuff was computed before. And we did the angular momentum loss, which involved some additional functions. And okay, they all look the same if you're not too careful. There are some polynomials and an arcsinch and whatever, some numbers out here. But this is the calculation of the energy loss and the angular momentum loss to order G cubed. Now, the G squared contribution was done previously to all orders in V by Binney, Damour, and Geralico, and we agree with that. The G cubed contribution was done by the same group, but in the PN expansion, so they did the first three terms, G cubed over V, V, and V squared. And if you take the results on the previous page, this thing, which is true to all orders in V over C, and expand out, the first three terms agree with what they have, but we have higher order, we have the full expression in V. There's a disagreement in the literature with just the G-squared contribution by two other groups. And, oh, I should say one thing. So there are two reference frames which are commonly used. One is the one I drew here, which you could think of as like the center of mass frame, where the particles are coming in with equal and opposite momentum. And the other commonly used frame is the rest frame, where one particle is at rest and the other one is moving. And you can't so anyway, we disagreed. So these groups did things in the rest frame and then got a result in the, in the center of mass frame and converted to the rest frame. And well, they got it wrong, basically, because of the fact that the asymptotic form of the metric is only valid, which I wrote earlier, is only valid in the center of mass frame. And we can convert because of our form factor formalism from one frame to another. And one of the problems which comes in is that when you do, maybe I should draw this here. So if you do, so if you think of a graviton radiation and then some higher order graviton radiation, this particular thing has a delta function of omega in it. It's like a static contribution which has a zero frequency piece in it. This is like the analog of the Coulomb potential. If you had just QED and you were emitting a photon, just a particle going along, it's just the Coulomb field. And you have to keep this piece. There's an interference of the delta omega from this diagram with the arbitrary, there's some, whatever the tensor is for here with the n omega. And you have to keep the cross terms and the omega equals zero piece, the static piece of the calculation, to get the correct answer. So, so part of the problems in the literature were people were ignoring the static contribution, and that's connected with the fact that you have this 1 over r squared Coulomb potential, which can interfere with a 1 over r radiation piece, and then the area of the sphere at infinity goes like r squared, but there's an extra factor of r in the definition of angular momentum, which compensates for that. Okay, and then, okay, Chashan made a little movie for me. It doesn't tell you too much, but it's still useful to see these things going around. So Horn and Burke worked out the radiation reaction force from the energy and angular momentum dissipation. And because we now have our angular momentum calculation plus Enrico and people's calculation of the energy loss, you can calculate the, okay, I'm not going to be able to restart this movie, but of the energy loss, you can calculate the radiation reaction force to high order. And here he just plotted what happens in a circular orbit to, if you don't have any radiation reaction, of course, you just keep going in the circular orbit. The red dot is what happens if you include radiation reaction. And of course, the thing in spirals. And if you notice what is happening, the red dot is ahead of the blue dot. And that's because in gravitational systems, when you lose energy, things move faster because of the minus sign between total energy and kinetic energy. And so this is some a numeric set starting at an initial radius, which was 15 Schwarzschild radii. You can't really see the difference between the leading order calculation and the V over C to a high power, because in this simulation, at least V over C was a quarter. So the corrections are small in this particular case. But clearly, as you go in, as this in spiral continues, as V over C gets larger, these effects will be more important. Okay, so maybe the most surprising thing is that somehow by doing Feynman diagrams plus this expansion, you can actually do better than the classical. It's a classical problem. You're really doing quantum field theory and then expanding out integrands. And it's a little bit mysterious how you can actually do better that way than by just perturbing classical field equations to get the corrections. And some of it has to do with the fact that there's a lot of technology developed for Feynman diagrams, and these particular kinds of integrals were studied previously in like NRQC. NRQCD just stands for non-relativistic QCD. So some of the technology and ideas from there have been applied in a completely different way. And I mean, the ideas are not ours, they're from Cliff and Zvi Baron and people, but we applied it to the angular momentum case where there's this additional subtlety with the zero energy piece, which had to be treated. And so we got something productive done during COVID, I guess. And this is, so I'll stop here. Thanks. Yeah. John.
Oh, sorry.
Yeah, I have a comment and a question.
Okay.
The comment is that there's a intermediate regime or something in between the examples we discussed, like gravitation, which has some of the same features, namely Mills theory.
Yes.
Where for reasons you explained for gravitation, for example, the total color charge in the region is the integral of the local density.
That's right.
The question is there some regime of QCD where it is instructive to study the classical laws of energy and angular momentum, but maybe in the large N limit or something like that?
Well, we were thinking of just working with classical Yang-Mills, because what happens is you can see that you need this 1/r cubed pieces effectively in the, and so from the non-abelian coupling, so if you have 1A and then here another one splitting, and if these things are falling off like 1/r, this splitting can give you a 1/r² contribution, and there may be some non-abelian flux, a flux coming from the non-abelian term at infinity. So we're looking at that to see if there's any extra contribution. Whether nonlinearities in the field equation can also give a contribution, which we haven't sorted out yet. So I don't know. There's another, okay, I stayed away from this, but I'll make a comment, which is actually from a paper with Jaffe from 1990 or something. Anyway, which is when people are working on the spin prop, what is called the proton spin puzzle. And they would like to write the proton spin as the gluon orbital angular momentum plus the gluon spin plus the quark orbital angular momentum plus the quark spin. As far as I can tell, there is, despite the fact that there's lots of experiments measuring this, there's no sensible gauge invariant way to do that combination, because you could see that in E&M, the answer is R cross E cross B. You can't break it up into two pieces. Okay. And so there's probably hundreds of millions of dollars spent on trying to break this up. Okay, because that's what people would like. But in field theory, it's not there. You can see that the x nu, that's the angular momentum. That's it. There's no extra plus some whatever, some Lorentz generator or some rotation generator. It's not there. And so, yeah, but there's some features with Yang-Mills we wanted to study, especially with the non-abelian nature. Yeah.
So the fact that you can emit angular momentum radiation without energy suggests that if you emitted that angular momentum or not, would give you like two different states that are the same energy, differing by stuff at infinity, which seems like it would connect with the BMS design.
I could not understand the BMS paper. Okay.
There's a connection.
There may be, there may not be. I have no idea. I can't understand what they're saying. There's a paper by Parati. Yeah, and from what Zvi told us, he agrees with us. Reading the paper, I can't see whether there's a connection, whether he agrees, whether he doesn't, or whatever. Yeah.
Well, the zero frequency on magnetism.
Right. Exactly.
Okay. But you want to stick with the Minkowski. You don't want to go to a rotating frame, right? Because you would have a problem.
Can you see if there's any questions on Zoom?
I can't,
Yeah, if we get on-
maybe I can, let's see. How come it doesn't let me quit? Ah, there, okay. Nope, I don't see anything. Well, I had my volume on anyway, so.
Kind of like this question, although much more naive. If I have angular momentum radiated without energy, and I have an angular momentum antenna that picks that angular momentum up, say, maybe starts spinning, how do I transfer rotation without transferring energy? I guess to me, rotation always applies some kinetic energy to rotation.
Okay, so here's the exercise, right? Take that problem in Feynman volume 2 and work it out. And so what's happening is that the cylinder is far away. So there's an R there in the definition of angular momentum. So you can get some energy transfer, which is order 1 over R and goes away. So that for the cylinder, okay, let's try it. I'll get it wrong, but it's fine. Right, you have a, so what is, who knows what the moment of inertia is? It's just mr squared, I guess, right? And so the kinetic energy is omega squared over 2mr squared, right? Omega squared over 2I. And so, I'm sorry, not, it's J squared over 2I. So it's G. Okay, and now, so you can have a non-zero J, but because R is so large, it's going to 0. So it's not, doesn't have to rotate, it's rotating with an infinitesimal angular velocity, and that's enough to get angular momentum, but not big enough to get energy because it's MVR versus MV squared. So if V goes like 1 over R, you're finite here, but this is 1 over R squared, and it's 0. I mean, the thing which was confused, okay, so if you do it in terms of Feynman diagrams, we're kind of used to thinking of this as gravitons or photons or whatever, and then you're doing some cut diagrams, but you can't think of this as photons. You have to keep the Coulomb piece, which is not in the not in what you would call the A's and A daggers when you quantize E and M. And you need that to get a correct answer.
One more question?
Also connected with this question. So in your result, we can angular momentum without with the energy. It will be consistent with the story that came out of the BMS analysis that you can have many different vacuum for asymptotic class spacetime where essentially you can, but all of these have the same energy.
Yeah.
But they all have
Yeah, so you could move from one to the other and get angular momentum. Yeah, I think so.